Provided some conditions are satisfied, the extreme value theorem guarantees the existence of maximum and minimum values. But how am I supposed to find those maximum and minimum values? We've actually already done this in some examples, but it's worth describing an explicit process for finding maxima and minima. Here's a four-step process. First, differentiate your function, then find all the critical points. Those are places where the derivative is equal to 0 or the derivative isn't defined. And also list the endpoints if they're included in your domain. Check those points, right? Check the endpoints, check the critical points, and potentially you also need to check the limiting behavior if you're working on an open interval. Let's work an example. Okay, let's work an example. Let's look at the function given by the rule f of x equals 1 over x squared minus 1, this quantity squared. But let's only consider this function on a restricted domain. Let's consider the maximum and minimum values of this function on the interval between -1 and 1, this open interval. And now I differentiate. Yeah, the first step is to differentiate this function. So before I differentiate it, I'm just going to rewrite this. Instead of 1 over x squared minus 1 squared, I'm going to write this as x squared minus 1 to the negative second power. It's going to make it a little bit easier for me to think about the derivative. So what's the derivative of this function? Well, by the power rule and the chain rule, this is negative 2 times the inside, x squared minus 1, to the negative third power, times the derivative of the inside, which is 2x. Or another way to write this is negative 2 times 2x, that's minus 4x, divided by x squared minus 1 to the third power. With the derivative in hand, I can find the critical points. Yeah, the next step is to list the critical points and also the endpoints if they're included. So let's see. What are the critical points of this function? Well, those would be places where the derivative doesn't exist or the derivative is equal to 0. Let's first think about when the derivative is equal to 0. Well, in order for that derivative to be equal to 0, it's a fraction. When is a fraction equal to 0? Well, that occurs exactly when the numerator is equal to 0. So I'm really just asking, when is minus 4x equal to 0? And that's just when x is equal to 0. So the only time when the derivative is equal to 0 is when x is equal to 0. Now, the derivative doesn't exist when x is equal to 1 or when x is equal to minus 1, but the function's not even defined in that case anyway, and I'm only considering numbers between -1 and 1 anyhow. So I don't have to worry about those. And I don't have to worry about endpoints because, again, the interval that I'm considering doesn't include the endpoints. It's an open interval. So I'm just going to check x equals 0 to figure out what's going on there. So let's think about this point where x is equal to 0. Well, the derivative at 0 is equal to 0. If I just plug in 0 into this, I can see that. What's the derivative at a number between -1 and 0? Well, if I plug in a number between -1 and 0, x squared is then between 0 and 1. So x squared minus 1 is now a negative number cubed. The denominator is negative. But this is a negative number, negative 4, times a negative number. So I've got negative times negative divided by negative. That's negative. So the derivative at a number between -1 and 0 is negative in this case. And a similar kind of reasoning will show that the derivative is positive if I evaluate the derivative between 0 and 1. So here's the deal. I've got one critical point on this interval between -1 and 1, and the function's decreasing between -1 and 0, and it's increasing between 0 and 1. So what does that mean about the point 0? Well, it means that the point 0 must be a place where the function achieves a local minimum value. So I can summarize that here. F of 0 is, this is the first derivative test, is a local minimum value. What about the end behavior? What happens when x is near -1 or when x is near 1? So that's really step 4 in this checklist, is to check the limiting or end behavior of this function. Well, what do I mean by that? I really mean look at this when x is just a little bit bigger than -1 or when x is just a little bit less than 1. Right? That's the end behavior of this function. These endpoints aren't actually included, so of course I can't evaluate the function there, but I should still see what happens when x is close to these endpoints. Well, let's imagine that I was trying to draw a graph of the function, right? What do I know from the derivative? I know the function's decreasing here and increasing here, and I know the function's got a local minimum value here by thinking of the first derivative test. So the function's going down and then it's going up. But what happens at these two values when I get close to -1 and when I get close to 1? When I get close to -1, the function is very, very large. And when I get close to 1 on this side, the function's also very, very large. So if I imagined trying to draw a graph of this function, right, it would be coming down like this, flattening out, and then it would be getting very, very large again. Let's summarize the situation. This graph will help us to summarize the situation. Right? What do I know? I know that f of 0 is the smallest output. It's the minimum value that the function achieves on the domain open interval -1 to 1. And there's no maximum value. By considering this limiting behavior as x approach to the endpoints which aren't included in this domain, I can see that this function's output can be made as positive as I'd like. Right? I can choose values of x to make the output as big as I want. So I can't say that this function actually achieves some maximum output value. It doesn't achieve a maximum output value, but it does achieve a minimum output value right here when x is equal to 0, and that output is 1. It's important to emphasize that the domain truly matters. Yeah, what if I asked to find the maximum and minimum values of the same function, f of x is equal to 1 over x squared minus 1 squared, but on a different domain? What if I looked on the interval from 1 to infinity, this open interval? Again, we start by differentiating. Well, of course, the derivative's the same, right? The derivative of this function is still minus 4x over x squared minus 1 to the third power. Now, where are the critical points? The only place that this derivative is equal to 0 is when x is equal to 0. And the only place where the derivative doesn't exist is just places where the function isn't even defined, right? So on this interval from 1 to infinity, there is no place where the derivative isn't defined or is equal to 0. So there's no critical points. So what about the behavior near the boundaries of this interval? What happens if x is just a little bit more than 1, or when x is really, really big? So we're working on the interval from 1 to infinity, this open interval. So that means the limits I should consider are the limits of the function as x approaches infinity, and the limit of the function as x approaches 1 from the right-hand side. And doing calculation, I find that the limit of the function as x approaches infinity is 0, because in that case the denominator can be made as large as I like, which makes this ratio as close to 0 as I'd like. And the limit of the function as x approaches 1 from the right is equal to infinity, because in that case, if x approaches 1 from the right, this denominator can be made as close to 0 and positive as I'd like, which makes this ratio as large as I'd like. So in this case, this function on this domain doesn't take a largest value and doesn't take a smallest value. The function's output can be made as big as I'd like if I'm willing to choose x just a little bit bigger than 1. And the function's output can be made as close to 0 as I'd like if I'm willing to choose x to be big enough. In other words, the domain matters. I mean, this function, if I'm considering the function on this domain from -1 to 1, it does have a smallest output value. It achieves its local minimum value when x is equal to 0. But if I consider the same function, but on a different domain, there's no critical point on this domain, right? And I studied the limiting behavior as x approached 1 and as x approached infinity, and I found that I could make the output of this function as large as I'd like and as close to 0 as I'd like. So this function doesn't achieve a maximum or minimum value on this interval.